Well, good morning and good afternoon, everybody, and welcome in for a super exciting Exploring by the Seat of Your Pants awesome day. For those joining us for the first time, and there are quite a few of you today, we are all about bringing conservation, adventure, and science into classrooms around the world, and you're catching us on a particularly exciting day because every February, since we were founded back in 2014, we kick out all the dudes and spend the entire month solely showcasing the most amazing women in science and exploration on planet Earth. And we do that because of today. February 11th is the International Day for Girls and Women in STEM. There's all sorts of celebrations happening around the world, and we always blow the roof off the place with some of our favorite people coming on for the broadcast. So today is no exception. We're going to dive in with two incredible broadcasts now and right after this with some of my all-time favorite scientists. Before we dive in, I want to note a few quick things. Number one, we do have a Kahoot today. So between our talk and our Q&A, if you want to play along with a little 4-question quiz to test your understanding and have some fun, you can pull up that game pin and join us. A little extra way to keep it interactive. I will also note and will share with classes at the end, if you're keen on amazing resources for girls and women in STEM, ifthenshecan.org cannot be beat. It is the greatest initiative of all time with all sorts of amazing videos, programs, everything. Wendy's involved in that too. You're in for such a treat. It's so cool. Can't get enough of it. Can't encourage it enough. And we will share that with all of you. Now, as I mentioned a name, we've got Dr. Wendy Bohon joining us today. She is an earthquake geologist. She gets to study the earth ripping apart. And if there's a cooler job than that, I don't know what there is. So I'm going to bring her in a minute. I will note we had a little bit of a tech fun thing today. So I'm going to be playing her presentation. She's going to have to say next for me as we go throughout, but she's so charismatic, you won't even mind. And with that, I'm going to zip it. Wendy, welcome to the broadcast. Nice to see you again. Great shirt. I was saying before we went live, best. It befits the earth that we're going to be talking about today. And take us away.
For having me. And hi, everybody. I'm so happy to be here today to talk to you about my favorite topic, earthquakes. And I've never actually given this presentation before. I made it special just for you all. So I want you to let me know what you think. Today, we're going to be talking about megaquakes, the science behind the world's largest earthquakes. And as I said, I'm Dr. Wendy Bohon. I'm an earthquake geologist, and I work for the California Geological Survey. I'm in charge of the seismic hazards and earthquake engineering branch. So next slide. And let's play that video. So this is a video showing earthquakes around the world. And once the video starts going, you'll be able to see, you got to click the little button at the bottom to make it go. There's a...
I'm going to figure it out, Wendy. I'm a master
maybe it won't. It doesn't really matter. We can look at this slide like it is. Do you see how there's those white dots all around? Actually, they're all different color dots. Those are earthquakes. And if you look, sort of squint your eyes, can you see that they kind of make a pattern? Do you see the pattern? Yeah. It may not have transferred as a video, and that's okay. We can still see the pattern. Who sees the pattern? Raise your hand.
See the pattern.
You see the pattern? That pattern forms the outline of the tectonic plates. Next slide. So the surface of the earth is covered by a thin skin of rock called the crust, and it's broken up into these big puzzle pieces that are moving around very slowly. In this picture, you can see all of those different colored pieces. Those are different tectonic plates. The arrows that you see are showing the direction that the plate is moving, and the length of the arrow is showing you how fast it's going compared to the other plates. So let's look at some of these. If we look at the yellow plate, we go back, you can see that the arrows are moving it towards the left-hand side of the screen, and they're long. That's the Pacific plate, and it's moving really fast. And if we look at the blue plate in the middle, the Nazca plate, you can see the arrows are moving the total opposite direction, but also really fast. So the area between the Nazca plate and the Pacific plate is moving apart. But if we look right next to the Nazca plate at the purple plate, the South American plate, those arrows are moving in a different direction. The Nazca plate is slamming in to that South American plate. So next slide. Because these plates are moving around in different ways, they're causing the plates to crash together in different ways. And that forms different kinds of boundaries. So if we look at the bottom left, that is showing an area where the plates are moving apart. They're pulling apart. This is called a divergent boundary. So remember, we were talking about the yellow plate and the blue plate and how they were pulling apart. If you look, the area between those two plates is red. And so on this map, all of the areas in red are areas where the crust is pulling apart. Those are divergent boundaries. Okay, now let's look at the little image in the middle. That is a place where you have two plates that are slamming together, like what's happening with the Nazca plate and the South American plate, which were the two other plates that we looked at, the blue one, and I think it was purple, right? And so when that happens, you form mountains. So the Himalayas are along one of these convergent plate boundaries. The Andes Mountains are along one of these convergent plate boundaries. And if you look at that middle image, you can see that in some cases, one of those plates gets squished down, jammed down underneath the other plate. And that's called a subduction zone. So that's a big hint. Keep that in your mind, a subduction zone. Okay, the next way that the plates can come together is called a transform boundary or a strike slip boundary. And that's where they're actually sliding past each other. And on this map, that's marked in green. And so if we look, there's not a lot of areas that are in green, but there are some, and they're very important to me personally. I live in California, which is right along one of those green boundaries, more commonly called the San Andreas Fault. Okay, let's go to the next slide. So as these plates are coming together in different ways, they form different kinds of faults. So is this one going to work? Let's see.
We're going to see. I'm going to try and get it to work for us because they all worked earlier.
If it doesn't, that's okay. Here we go. This will.
Oh, here we go. Yep.
Oh, nope. Go back.
Go back. Sorry.
It's all right. If we pull the plates together or pull the plates apart in those divergent boundaries, it's going to stretch them. And see the one on the left-hand side, how one side has dropped down? That's called a normal fault. In the middle, if you smush them together, one plate is going to jam up over top of another or slide down underneath the other. And that is called a reverse fault or a thrust fault. And then on the far side, on the right, that's where they're sliding past each other. And that is a strike slip fault. Okay, next slide. Let's see if this one will work. This is just showing you how exactly that works, where they pull apart.
So trying for you.
We're going to have so much time for questions, you guys. It's going to be amazing. That's all right. Okay, so let's just go past these. It's just showing the same thing. Yep. It slams together or it pulls apart and it makes different kinds of faults. So I am very certain. Keep going. These different faults will cause earthquakes. So as the tectonic plates are moving, it builds up stress and strain inside the earth. Okay, and when that stress and strain overcomes the strength of the rocks, it causes them to break. Just like when we're under stress, oh, we can break. That happens to the rocks too. Does this one work? I don't know why these aren't working.
I don't know why either. I can try and download it and see if we can get them working that way. I'm going to do that in the background and see if we can get some of the things going, but you can keep us going while we're doing that.
Sure thing. So when the stress and strain overcomes the strength of the rocks, then the rocks will break. That sends out energy waves in all directions. And those energy waves are what we feel is shaking. That's what we call the earthquake, right? Is the shaking. But what it actually is the rocks breaking. Next slide. This is the most important part, you guys. So I need you to pay attention to this part, okay? When we think about earthquakes, we usually think about what's happening to us up here on the surface of the earth, but earthquakes actually start deep below the surface at a point called the hypocenter. And they break the ground over a whole surface called a rupture surface. And so I have two pieces of rock I'm going to show you right here, okay? So we have these two pieces of rock and they come together at a surface right there. That would be like the rupture surface. And when the fault breaks, it breaks along that whole surface. So if we have, let me get it a better way. If we have a strike slip fault, they're going to go like this. If we have a normal fault, they're going to move like this. If we have a thrust fault, they're going to move like this. But the important thing is the area of this surface. Every single point on that surface releases energy. And so do you remember how to calculate area? It's a quiz. Do you remember your math? Area is the length times the width. And in this case, it's the length of the fault plus how deep the fault goes into the ground. So the more area that breaks, the bigger, the larger magnitude earthquake we're going to have. So a bigger fault means a bigger earthquake. So when we're talking about mega thrust earthquakes, what we're actually talking about are giant, giant faults. Okay, next slide. Now, if you remember that, oh, this is what's happening. I forgot I put this in here. Is it going to work? Is it going to work? It's a test. Nope. Okay, go to the next one. Okay, because I had put that one in last minute. Remember when we were looking at the image that had the three things on the bottom, and some of it was blue, and some of it was red, and some of it was green, showing the different plate boundaries? This is the area where there is a blue plate boundary. So if you see that blue line running across there, that is the Cascadia subduction zone. That runs from Northern California all the way up along the coast of Oregon and Washington into Canada. All right. But it's not just that blue line that we see, it's also that plate diving down underneath the other plate. Okay, now I want you to think about something that everybody loves. Shut your eyes and imagine chocolate chip cookies.
Yes.
Okay, you're pulling chocolate chip cookies out of the oven, they're still hot. You pick one up, it's gooey, it flops over, it's bendy, right? But you have to leave them on the table because you don't want to burn your mouth. So when you come back, you pick one up and it breaks because it's cool, right? Okay, open your eyes. That's what's happening here. When you have a plate that's diving down underneath the other plate, that plate is like a cold chocolate chip cookie. It's brittle, and so it can break. If it gets too warm, it gets mushy and it doesn't break. And if it can't break, it can't have earthquakes. And so when we have these oceanic plates, they are cold, they are dense, and they can break. So we get earthquakes that go really deep inside the ground and they're really long. So they're the ones that create these megathrust earthquakes. And so if we go to the next slide, what we're seeing here is an example of a megathrust earthquake that happened January 26, 1700 at 9 o'clock p.m. So the map that you see over there, those different colors are indicating the levels of shaking in different places. Every earthquake has one magnitude, in this case, a magnitude 9, but it causes the ground to shake with different intensities in different places. And so the areas you see in red and orange, those shook violently, very strongly. Areas in blues and greens still felt that shaking, but it was more moderate or light. This is really strong shaking all the way from Canada into Northern California. That's a huge area. But I want you to think carefully. I've said some strange things here, right? This occurred on January 26, 1700 at 9 p.m. How do we know that? That is a very specific time. Now, we do have the First Nations, indigenous people in this area, did give us a lot of information about this earthquake, but it was a geologic mystery that we solved as recently as the late 1980s and early 1990s. So it was a geologic mystery. Next slide. What we saw, so here's some lines of evidence that we used to figure out what was happening. Let's look at the top at those different kinds of dirt that are up there, dirt and soil. This is a classic layer cake deposit from a tsunami. On the bottom, you have dune sand, like sand dunes. On top of that, that black layer is topsoil. But on top of that, you have sand. And then on top of that, you have tidal mud. That's not what you would normally see unless there was a tsunami. So that sand was deposited by that tsunami in 1700. And so geologists were like, interesting, there was a tsunami here. I wonder where it came from. So then they started looking all up and down the coasts of Oregon and Washington, and they're seeing this deposit in all these different places. And then they started seeing something else really interesting. They also said, we're seeing these things called ghost forests. If you look down at the picture down there, see those little stumps that are sticking up? That is a ghost forest. It's the remnants of dead trees. And they found these up and down the coast. And they said, we know that these can form because of tsunami. Here's another line of evidence that there was a tsunami, but when did it happen? So they started looking at the tree ring patterns. Trees only form their rings when they're alive, right? Once they die, they're not making any more rings. If you look over on the right-hand side at the bottom, at the top where it's sort of yellow and orange, those are tree rings from a living tree. And at the bottom, the brown one, those are tree rings from a dead tree found in one of these ghost forests. And the last ring in that tree was made in 1699. And when they looked up and down the coast of Washington and Oregon, they found over and over again that most of the trees had died in 1699. That is so specific. And they thought, okay, that gives us better timing for when this tsunami happened. And it must have happened nearby because of the pattern of the way the ground moved. So what was the final kind of understanding? Where did that come from? From all the way across the ocean. Next slide, please. So Japanese samurai, merchants, and people that lived along the coast recorded an orphan tsunami on January 28th, 1700. An orphan tsunami is where there is no parent earthquake, no shaking that warned coastal villagers that a tsunami was coming. Geologists think the parent earthquake that caused that tsunami that was experienced in Japan happened in the Pacific Northwest. But why is that January 28th? And I said it was January 26th. Well, the earthquake occurred late in the evening, right? It takes about 12 hours for tsunami waves to travel across the Pacific Ocean from the Pacific Northwest to Japan. If we take that into account, and we take into account the differences in time zones, that tells us that the earthquake happened January 26th, 1700 at around 9 p.m. It was a great geologic mystery that looks like it has been solved. But this is just one example of a mega thrust earthquake, one of the largest earthquakes that happens. Let's talk about some more of those. Next slide, please. Oh, nope. Let's see if this one works.
Oh, it's going to try. I'm gonna.
Right.
I want to stress for our audience too, Wendy. We had this working like a minute before we went live, and it just entirely failed me the moment we went live. So I don't know.
That's
if
okay.
I'm gonna try and find these videos for folks after, and I can get the whole slide deck to every class as well if they'd like to watch the videos.
But that's okay. If this doesn't work, I have other things in there that were to reinforce the concept. So
sweet. I think we're gonna.
Right. Okay, go to the next one because this is showing the exact same thing, just a different way.
Cool.
So this is showing the tsunami that was generated by that earthquake in 1700. And so what these different colors represent are the height of the wave or the maximum tsunami amplitude, and it's measured in centimeters. So the areas that you see in black down to red, those are the areas where the tsunami waves were the highest. And you can see if you look along Oregon and Washington, that's where the colors are the darkest. So the areas that are close to where the earthquake happened are going to be the ones that experience the strongest tsunami, the highest tsunami. And they're also the ones that are going to have the least amount of warning. All right, next slide. Let's look at some other ones. In 1960, there was one of these mega thrust earthquakes in southern Chile. It was a magnitude 9.5. This is the largest earthquake ever recorded. It broke 700 kilometers of that fault that runs along the boundary between the Nazca Plate and the South American Plate, and it moved the ground as much as 40 meters in some locations. It killed more than 1,600 people, injured 3,000 people, and caused almost $500 million of damage in southern Chile. Next slide, please. This earthquake also generated a tsunami. Okay, so the tsunami from this earthquake was up to 25 meters high in Chile. It caused a lot of damage across the Pacific Ocean. So it caused 61 deaths, $75 million of damage in Hawaii, 38 deaths, and $50 million of damage in Japan. 32 folks were dead or missing in the Philippines, and it caused $500,000 of damage to the west coast of the United States. And you can see the picture that I've put there. There are multiple tsunamis. The one on the top is from the earthquake we're talking about, that magnitude 9.5 that happened in 1960. There was another earthquake in 2010, a magnitude 8.8. That is the tsunami wave from that one in the middle. At the bottom is the tsunami generated from a magnitude 8.2 in the same area in 2014. So these earthquakes that I'm telling you about today are just a sampling of some of these really big earthquakes that happen along these subduction zone boundaries. Next slide, please. The next one was a magnitude 9.2, and it happened in Alaska on Good Friday in 1964. This one broke 970 kilometers of the boundary between the North American plate and the Pacific plate. It moved the ground 20 meters in an instant. Property damage from that earthquake was estimated at 116 million when it happened, which would be almost $1 billion in today's money. Next slide. The tsunami from this earthquake was really interesting because it caused huge waves very close to where the earthquake happened. So one of the features or the factors in how big a tsunami is going to be has to do with the shape of the land and the shape of the ground underneath the ocean, in addition to how much the ground under the ocean moves. So tsunami in a particular bay in Alaska was 67 meters high. There were 139 people killed because of this earthquake and tsunami. Only 15 died as a result of the earthquake, and the rest died as a result of the tsunami. And those folks were in Alaska, Oregon, and California. Next slide, please. The next one that happened was the Indonesian earthquake. It was a magnitude 9.2 that happened on Boxing Day in 2004. So in this image, if you see the area in green, that's the area that broke during the earthquake. So you can see it was a really long fault, but it was also had like if you think about how the fault went down into the earth, it also went down and was able to be broken for a long distance inside the earth. This fault broke between 13 and 1,600 kilometers of the fault and moved the ground 15 to 20 meters. Next slide, please. The most devastating part of this earthquake, however, was the tsunami that it generated. It caused waves up to 30 meters, which killed more than 250,000 people in 14 different countries, especially in Indonesia, Sri Lanka, India, and Thailand. And all of these previous examples that I've told you about, the biggest problem with the tsunami and the reason that so many people died was because they didn't have any warning that the tsunami was coming. Next slide, please. In 2011, there was an earthquake off the coast of Japan called the Tohoku-oki earthquake or the Sendai earthquake. It was a magnitude 9.1 that broke 400 to 500 kilometers of the fault, all the way down to a depth of 200 kilometers. Some of the areas of the fault moved up to 80 meters, which is the largest value of movement ever recorded during one of these earthquakes. The seafloor lifted up by 10 meters, and this earthquake and tsunami caused almost 20,000 deaths and 6,200 injuries. Next slide, please. So this is a video.
I can actually bring this up. This is the airport.
Okay.
I can bring this up from the last time we did this. And
oh my gosh,
to the airport, but it's super cool. Cool. So let me cue that up
this
for people, and you can see it.
Yeah, this is a video that shows the shaking in the Sendai airport from that earthquake.
It's like truly alarming, Wendy.
Yes. And the ground shook like this for more than 6 minutes. All right. Thank you for bringing that up. Well done, pulling that up so quickly. All right. So next slide.
Let me get that up. Yeah, now we're going back. Perfect.
Yep. So that was the ground shaking. This is the tsunami that was generated from that earthquake. There was a wave height of up to 39 meters in part of Japan. By the time the waves crossed the Pacific Ocean and reached Chile, they were about 2 meters high. This caused severe damage in coastal Japan, damage around the world, including, $100 million of damage in California. And in Japan, it also caused the Fukushima nuclear disaster, which was really, really terrible. So it was a devastating tsunami. But by that point, we had put some measures in place to help people around the Pacific know that tsunamis were coming. Next slide. So this is that tsunami coming into the Santa Cruz Harbor in California. It caused $100 million across California and $28 million in damage just in this harbor right here. So you can see that a tsunami is not this big breaking wave, the way you might think of it in, movies or whatever. It's almost like a big flood or a tide that's coming in really quickly and then just doesn't stop. Next slide, please. So if we think about all of the places where we were just talking about earthquakes, and I'm going to test Jesse on his geography. Okay. The first one was the Juan de Fuca plate. So where is that? Can you put your cursor on it?
Oh, I can. How do I put my, oh, there it is. There we go. I can put my cursor up here.
Yes, you're winning.
There we are.
That area is blue, that little section. Okay. The next one was the South American earthquake, right? In Chile, the 1961. Where is that? Put your cursor on it. Excellent. That area is also blue, which means it is a convergent boundary. The next one that we talked about was the 1964 Alaska earthquake. Where's that border? Up at the top. Yes, also blue. And then the next one, this was going to be kind of hard because the way this map is, was in Indonesia. Where's Indonesia on the map? Everybody be pointing. Yes, right over there. That boundary also blue, a convergent boundary. And the final one was in Japan. Yes, over by the Philippine plate, also blue. So all of these earthquakes happened on these convergent plate boundaries. So the largest earthquakes in the world, these mega earthquakes, happen on these convergent plate boundaries. Next slide, please. And so what can we do? I mean, I just gave you a lot of really scary information, right? These were big earthquakes that caused big tsunamis and people were hurt, and that could be scary. We're doing a lot to make sure that we can protect lives and protect property. So this image is showing seismic stations that are part of the global seismographic network. So each one of those dots is showing the location of a machine that records earthquakes. So we're always listening, always recording all of these earthquakes. And that helps us to figure out where an earthquake has happened and how big it is within moments of it occurring. And this is just one of many seismic networks from around the world that are doing this kind of earthquake monitoring. Next slide, please. We've also put out something called DART buoys. So this map down here that has those little diamonds in different colors, those are showing the location of these deep ocean assessment and reporting of tsunamis buoys. And the idea here is that these are measuring the height of the waves and also the pressure under the water. And they can tell us not only that a tsunami is coming, but they can tell us about how big that tsunami is going to be. And so if we think about the places where we were just talking about those earthquakes, off the coast of South America, there are buoys. Off the coast of the Pacific Northwest, buoys. Indonesia, buoys. Japan, buoys. Alaska, buoys. So we now have a warning system, right? That was what was the problem with a lot of those earlier earthquakes, is that people that were far away on the other side of the world didn't know the tsunami was coming. And now they do. Next slide, please. We also have brand new technology that is helping us to both see and understand and measure tsunamis. So this is an image that was captured in December of 2025. If you look at that star showing the location of a magnitude 8.8 earthquake that occurred off the coast of Russia, right? Nobody over here in California would have felt that, but we could have been impacted by a tsunami if it was big enough. So what you're seeing there, those different colors, are showing the sea surface height. So basically the tsunami wave as it's coming out from that earthquake. But see that bright stripe across that? That's the really cool thing about this image. That's from a satellite called the SWAT satellite. And it actually was able to measure the sea surface and give even more information about that tsunami that we could then use to figure out whether or not it would be a tsunami that was big enough to cause problems. So now we can observe it with seismometers, we can observe it with buoys, and we can observe it from the skies using satellites. Next slide, please. All right, I don't think these are going to play. The idea here is that we can build to withstand tsunamis, we can build to withstand tsunamis too, but we can build to withstand earthquakes. And so these are different ways that we can construct homes and buildings to ensure that they can be much safer and can, weather that seismic shaking. So we can put things in them like these giant pendulums, tuned mass dampers that kind of absorb the energy of the earthquake. We can make sure to tie homes to foundations. We can make sure that buildings are built in such a way that they can bend but not break. So we can make sure that our buildings, bridges, dams, schools, and other infrastructure are safe from earthquake shaking. Next slide, please. So there's a lot of things that we can do. Just talked about some of them. We have earthquake hazard maps. That's the one we see in the middle for California. We have tsunami hazard zones. These are places where you could potentially have a tsunami. And then we have evacuation routes that are mapped so people know where to go, just in case there is a tsunami that's coming. So knowledge is power. Next slide. So what is it you really need to know? If you feel earthquake shaking, drop down to the ground, take cover underneath a sturdy object, and hold on until all the shaking is stopped. If you're at the beach, there are two possible ways you could get a tsunami warning. The first is an artificial way. That would be either an alert to a phone or maybe sirens blaring. But if you're on the beach and you feel strong or prolonged earthquake shaking, that is your natural tsunami warning. As soon as it's safe to do so, so when the shaking has stopped, you want to move inland or move to high ground or both. So the time that we need to prepare for tsunamis and for earthquakes is before they happen. So that's right now. We need to make sure we're building buildings that can withstand shaking, that we're putting out buoys that can tell us tsunamis are coming, and that we're educating people about what to do if they feel shaking or might be in the path of a tsunami. Because we don't need to be scared of earthquakes and tsunamis. We just need to be prepared for them when they do happen. And that's all from me. Thank you. This is my favorite picture of an earthquake. If the last slide, if you want to show that. It is not from the kind of earthquakes we were talking about. This is from an earthquake that happened in California in 2019. So, the kind that slide, the strike slip earthquakes. Yeah. This is what it can look like on the surface. And this is called a mole track because it looks like a giant mole burrowing underneath the ground. So
super cool. Oh, thank you, Wendy. And thank you for bearing with the crazy videos that were a big part that didn't want to play, but we'll highlight those to classes after. We're going to start with a little Kahoot together to test some understanding, have some fun, and then we're going to dive in with Q&A with all of you. And if you have extra questions when we're done, please do email them to me. I'll get them to Wendy. We'll keep the learning going when we're wrapped up the broadcast. But we are going to begin with those questions. So for those new to Kahoot, the faster you answer, the more points you get. And for those who've heard me say this before, what you win is Wendy and I's everlasting respect. So let's dive in with this. We're going to get underway. If you want to just yell out the answers in your class, that's fine too. And then we can have a nice long Q&A when we're done. We're going to go to Mrs. Coddington's class, Mr. Alston, St. Teresa's School, and Miss Dixon in that order, just so you know. Here we go. Question 1, true or false? If the earth were an apple, the crust we all live on would be about the thickness of the skin of the apple. It seems like the ground beneath my feet is thicker and stronger than that. I don't know. But maybe that's just in my fever dreams because I want to believe that it's thicker than that tiny little skin on the apple. What do we think, Wendy? There might be less of a job for you if the crust were thicker, Stay very still. Oh, look at this mix. So yeah, the crust on Earth is insanely thin. Like, it's quite unbelievable how thin the ground beneath our feet is. And we tripped up quite a few people with that. So Fabulous Eagle has our lead. We'll go to question 2. How many earthquakes happen every year? We talked about some of the biggest ones today, MegaQuakes, which is really fun to say. Is it 10, 100, 1,000, or considerably over 10,000? Wendy, is there an earthquake happening right now somewhere on Earth?
Yes, there is. Absolutely.
There more than one, maybe? Like, could be.
I have a couple of little facts for you after this that might blow your mind, but I don't want to give it away.
Ooh, look at this mix.
Oh, look at this.
I've never seen a chart like that. So considerably over 10,000 is correct. Wendy, tell us the cool facts.
So we record more than 10,000 earthquakes every year just in Southern California. Japan records more than 100,000 earthquakes every year. So.
But we learn what we do if there's any big ones ever. So that's really good. We design a lot of buildings in a lot of places that have a lot of them to withstand and not be dangerous to anyone. So I love that we get this question. All right. The Earth's surface, this should be a gimme. We talked about this a lot. And it's also in the picture. I wanted to give you guys like the confidence to know you could just all nail a question correctly. If you say the wrong answer, you do have, no, you don't have to leave. You're good. This is fun. We just want to reinforce the concept because scientists didn't know this. No one in the world had confirmed this until like the 50s, 60s. Like, I mean, it's remarkably.
It was like the 60s, yeah, before it became widely accepted.
So true is our correct answer. If you don't think so still, rewatch the presentation. Your mind will be blown by the end. Gentle Bear has a commanding lead going into our final question. Mrs. Coddington's class, we're coming to you in a minute. The biggest earthquake measured was a what? A 1, a 15, a 9.5, a 10.3. We talked about this. Might have been in Chile. Sure. Hint, nudge, nudge.
And it was the largest earthquake ever measured, but not necessarily the largest earthquake that's ever happened.
Because we've only been measuring really well for a lot less time. Ooh, a lot of people thought 10.3. So is there a limit to what an earthquake can get to, by the way? Like 9.5 is correct. Is there like an upper level?
Yeah, it would never get to a magnitude 10 or greater. 9.5, 9.6 is probably around the upper limit.
And I'm
based
sure
on the size of the faults that we have on Earth right now.
This is what we're going to get questions, I'm sure, that address this in some fashion, but we'll take our leaderboard first, and then we'll go to Mrs. Coddington's class. Happy Sphinx is heard. Fabulous Eagles second. Did our bear friend win with a commanding lead at the end? I think yes, Gentle Bear. If you are Gentle Bear, let us know where you are. Thank you so much for playing along. Mrs. Coddington's class, Stitchville, come on in, unmute your mic, and take us away. Oh, Stitch Shirt, hello. I love it.
Are there earthquakes on Mars?
Ooh.
What a fabulous question. So, no, they're called Marsquakes. Earthquakes are only on Earth. But yes, there are quakes that happen on Mars. We do call them Marsquakes. And there was a seismometer that was put on Mars by NASA called InSight that actually measured these. And so one of the reasons they wanted to do that was because we can use seismic waves to see what is inside of planets. Kind of like an ultrasound, you can see inside of someone's body using the waves from the ultrasound. We do the same thing with earthquakes or Marsquakes. And so we were able to see the inside of Mars and learn a lot about its crust, mantle, and core because of the Marsquakes. Great question.
It is a great question. And I want to stress, if you're really keen, about a week ago, we had Dr. Abigail Freeman on, who designs robots that go to Mars, and talked about Mars quakes with the robots they put on Mars. So a nice follow-up to this if you're keen on space. Very cool question. Our Cougar Cubs, Mr. Alston's class, unmute, come on in, grade 4s, and take us away. Hey, folks. Hello, so many hands. The best problem to have. Come on up, take us away. Run! No, you're good. Take your time. We got lots of time. Hello, unmute. Come chat with us.
Do earthquakes make wind?
Ooh.
Good question. They do not. But Aristotle thought that earthquakes were actually the result of wind moving around in giant underground caverns. So the idea that wind and earthquakes are connected has been around for a long time, but they do not make wind. But
That's
good question.
Sick Aristotle reference in a broadcast. We haven't had one of those in a while. St. Teresa School, we're coming to you. Mrs. Dixon's class, YouTube, and then we're going to try and do a whole other round as Wendy's whipping through these. Come on in. Hey, third graders.
Can earthquakes affect airplanes that are in the sky?
Great question. Fortunately, they cannot. So there's some funny stories about big earthquakes that have happened in California, and geologists that study California earthquakes were in airplanes and they missed it and they were sad. So they do not, fortunately, affect them, but volcanoes do. So volcanoes, when they erupt little pieces of rock everywhere that can really impact the engines of jets. And so there will often be aviation warnings around volcanoes that are erupting. But fortunately, earthquakes, we're all safe in the air.
Interesting track on these questions. We haven't had questions quite like this before, so thanks, everybody. I love these. Mrs. Dixon's class, we'll come to you in a minute. Unmute your mic, and we can come to you that way. We've got a really unique question on YouTube from Miss A's class. They're at Victoria Park Collegiate in Toronto. They want to know, if a city's surrounded by mountains on all sides, does it mean there have been made like many plates colliding? Like, does it indicate that there's like a plate boundary around them?
That is such an interesting question. And the answer is maybe. So usually when you see mountains, that means there is a fault at the base of the mountain. So there can also, though, be topography or uplifted ground because of something called isostatic rebound. So like in Toronto, right, you guys used to be covered by glaciers and by an ice sheet, the Laurentide ice sheet. And so it was smushing the ground down. And when the ice melted a long time ago, the ground is still moving back up again. And that can cause topography, and the ground may uplift at different rates in different places. But yes, that means that there are faults nearby, but that doesn't necessarily mean that it was the boundary of plates. But that is such a good question. And I'm going to be thinking about that for a little bit longer, because I feel like that's not a very satisfactory answer. I may get back to you guys.
It's a really neat answer. And the fact that you mentioned isostatic rebound, which everybody should look up, the idea that the earth just comes back up like this when the big weight's been put on it, just like a cushion would, is crazy. And I grew up in Toronto, so I love getting to think about this. Super, super neat stuff. Mrs. Dixon's class, unmute your mic again. Come on in. Hey.
Come closer. Do you know how many earthquakes have happened so far?
How many earthquakes have happened so far? Or no? Yes. How many so far? Oh, there you are. Hi, guys.
Oh my gosh. I don't know. So it's hard to say. That is such an interesting question. We can, if we're, say, looking at mountains, say we're looking at the Grand Teton Mountains, and we know about how much they grow every year, or how much they grow in big earthquakes. We can guess from the time those mountains were formed until the present how many earthquakes it took to make those mountains. But I have no idea how many earthquakes have occurred over Earth, because we would have to make some assumptions, right? We would have to assume that the number of earthquakes we see happening today are the number of earthquakes that have always happened. But the Earth didn't always look like it does now. So I don't actually know the answer to that. I do in the short term, but not over the whole history of the Earth.
Yeah, we stumped the expert. This is the joy of our Exploring by the Seat of Your Pants broadcast. So thank you for that question. We're going to do another quick round. We're going to do 5 more total questions. And if you have extra ones, please do email them to me. I'll pass them along to Wendy. We'll inundate her entire week remaining with extra earthquake questions. But Mrs. Coddington's class, come on back in. Take us away. Hi.
After an earthquake happens, does the land go back to how it was before, and is it by itself?
Good question. And that actually gets right to the heart of one of the questions that the geologists were asking after the 1906 Great San Francisco earthquake. So the stress and strain builds up inside the ground, and it will actually bend a little bit, and then it breaks. And once it's broken, it doesn't go back to the way it was before. It's permanently changed in that way. But through time, it will kind of erode, right? Wind and water and storms and things, little critters burrowing will change what the ground looks like. So we might not see the evidence for that earthquake the same way that we did right after it happened, but the ground does not go back to the way it was before.
Yeah, cool question. Thanks so much. By the way, we've just got comments about loving your shirt, and I just want to highlight them on camera because it is the best shirt we've ever had on in the history of our program. So thank you.
I wore it just for you guys.
Oh, Mr. Olson's class, we're going to head back to you guys. Come on in, grade 4s, and take us away. Everybody's got a question. Sweet. Unmute so we can hear you as we arrive. Hello.
Hey, Emma, come up here so they can see you.
Is there any earthquakes more powerful than the MegaQuake?
Ooh.
That's a good question. So we just call any earthquake that's really big kind of a megaquake, and it's almost like a Hollywood name. Geologists don't use that so much. We call them like megathrust earthquakes. So megaquake sounds like more cool. But I would say that when we're talking about the biggest earthquakes in the world, we just call them mega, and that's about as big as they go.
Yep. It's a great question. Thanks, guys. And please do email me more. We'd love to take them. I know you guys are really good for that. St. Teresa School, we're going to head to you. We'll take one more from YouTube, and then we'll wrap up with Mrs. Dixon in a minute. Come on in.
What was the biggest earthquake you have ever experienced?
Ooh.
The biggest earthquake I've ever experienced, it was a magnitude 7.8 in Mexico. I was in San Diego, and I felt the shaking from that earthquake. But I used to be an actress. I was not a geologist. I didn't always want to be a geologist. And I felt a big earthquake in California, the magnitude 7.1 Hector mine earthquake, which is the second biggest earthquake I've ever felt. And I was so interested in that earthquake and learning more about that earthquake that I totally changed careers and went back to school to study earthquakes.
Super, super cool. I love when we get to highlight your career story. It's fantastic. And if you want to see more of it, we have talked about it in some other broadcasts. We're going to wrap up with 2 more questions. So Mrs. A's class from earlier wants to know, why not bigger than a 10? So just to reiterate this, why can't we have an earthquake level 20?
It's a great question. So the magnitude of the earthquake depends on the area of the rock that breaks, because that controls how much energy is released. That's part of it. It's how much of the rock that breaks, how far it moves, and the properties of the rocks itself. And so we just don't have any faults on Earth that are big enough, long enough, deep enough to create earthquakes that are larger than maybe a magnitude 9.5 or a magnitude 9.6. Plus, the magnitude scale is logarithmic, which means the difference in energy released between a magnitude 5 and 6 is not the same amount of energy that's released between a magnitude 6 and 7. So if we think about it with spaghetti, if we imagine one strand of spaghetti is like a magnitude 5, a magnitude 6 would be 32 strands of spaghetti. That's like a whole portion size. That's like dinner. A magnitude 7 would be 32 times larger than that. That would be like an entire giant box of spaghetti, right? So the magnitude scale can be tricky like that.
I love when we get to feature that. It's really, really cool. It's hard to wrap your head around. Is there another example of that, like at that kind of scale that is in sort of everyday life for classrooms? I'm trying to remember back to Math like a kid.
I have one that's about time, but I'm not sure if I can remember exactly what it is.
Fair enough. There you go. Our earthquake schools, our scales, the one to remember for this. Mrs. Dixon's class, we're going to head to you with one final question. We just really appreciate all of you. I really can't encourage you enough. ifthenSheCan.org. This will be on our YouTube channel. A bunch of other amazing programs with Wendy are on that channel too, so you can explore so much about her and her work. We'll wrap up with one final question and then bring everyone in for a big thank you and farewell. Come on in. Hey, guys.
How many magnitude 9.5s have there been?
Ooh, magnitude 9.5s ever.
Well, there's only been the one that we've recorded that was in 1960, but we've really only been recording earthquakes for the last 120 years or so. And we don't expect that earthquakes that big would happen more than once every century. So we've only recorded one, but we would expect that there would be one about every 100 or 200 years. So there have been a lot, probably, but we've only seen that one. Thank goodness.
Thank goodness. And fascinating that we can know and track back that far. Again, the ability of scientists to do detective work into the past never ceases to amaze me in all sciences. It's one of my very favorite things of getting to be a broadcaster. Wendy, before we wrap up and say farewell, is there any final message about earthquakes you want to leave us with today, or megaquakes, as it were?
Yep. Earthquakes can be scary because they happen without warning. They can't be predicted, and they can be damaging and scary. So it's important to remember that we don't have to be scared of earthquakes. We can prepare for them, and we can make sure that we are safe from earthquakes and tsunamis. We just have to be ready for them. So it can be useful if you're going to be going to the sea or going to some place that has earthquakes to make sure that you know what to do. Drop, cover, and hold on when you feel earthquake shaking. And if you're at the beach and you feel strong shaking, move inland or up.
No better message than that. Hopefully our classes don't need to experience any big earthquakes in their lives. Fingers crossed. But we're going to bring in all our kids to say a big thank you and farewell. And a thank you, Wendy, for joining us on this amazing day, International Day for Girls and Women in STEM. You rock. You're the best ambassador ever. Mrs. Connie, the class, Mr. Olson,